Here, we are going to verify, given matrix A, if the corresponding eigenvector of A represented by x sub 1, together with its corresponding eigenvalue, represented by lambda sub 1 and lambda sub 2, are for the given specific matrix. So we have two matrices here, both represented by matrix A. And again, we're going to verify whether the given eigenvectors and eigenvalues with their corresponding eigenvalues are for the matrix A. To do this, we are going to represent, let's start with the first matrix and the first set of vector x and lambda. And we are going to use this method here. Let's have A, x sub 1. Let's try to solve the result when we multiply A, which is the given 1, 0, 0, negative 1, to be multiplied with our vector x sub 1 here. So you have 1 and 0. Okay. And the result of this can be represented by a certain result when we also multiply the given eigenvalue, okay, in this case lambda sub 1, times the eigenvector x sub 1. If we could represent the product of this by the product of the eigenvalue together with its corresponding eigenvector, then we have verified as such. So if we're going to multiply this, of course, this is a 2 by 2 matrix to be multiplied by 2 by 1, so the result should be 2 by 1. So you have here 1. You multiply this 1 times 1 is 1, 0 times 0 is 0, so you have 1 here. And then for our second entry, 0 times 1 is 0, negative 1 times 0 is also 0, 0 plus 0, 0. This is the result if we're going to multiply A by our first vector x sub 1. Let us see if we could represent this using the product of its corresponding eigenvalue and the said eigenvector. Of course, we can actually factor here a certain 1, okay? And it will still be the same vector here. Because if we're going to multiply this scalar 1 to all the entities here, it will just return to this expression or matrix. This means this is actually our lambda sub 1 and this is our x sub 1. In short, we have verified that the given vector x sub 1, which is 1, 0, with its corresponding eigenvalue of 1, is for this given matrix A. Now let's do the same thing for our second set of eigenvector and eigenvalue. So you have here A, x sub 2 in this case. The same thing, let's multiply our A, 1, 0, 0, negative 1, by our second vector, 0, 1. And we should reach an expression, or we can express the result of this in an expression by the product of your lambda sub 2, your eigenvalue, and its corresponding eigenvector. Of course, we multiply this, 1 times 0 is 0, 0 times 1 is also 0, and of course, again, this is 2 by 2 matrix, this is a 2 by 1, so the result would be 2 by 1, so that's 0. 0 times 0 is 0, negative 1 times 1 is negative 1, so you have here this expression. Now, we can express this, or we can look for an expression which is equivalent to this by multiplying a certain scalar negative 1 to 0 and 1. In short, we factored at negative 1. And if you're going to return multiplying this, that's just 0. And then negative 1 you will return here. This is actually our second eigenvalue. And this is our second eigenvector. This means that this set of eigenvector and its corresponding eigenvalue is also for this given matrix A. Okay? So we have verified both of them here for this matrix A. Now, we have another matrix A here, another set of eigenvalues and corresponding eigenvectors. Let's use the spaces here at the bottom. So let's do the same thing. For the first set, you have A, x sub 1. So you have A being 1, 1, 1, 1 to be multiplied with your x sub 1 of 1 and negative 1. And hopefully the result of this could be expressed as also as the product of our lambda sub 1 and x sub 1. this result here, okay? So you have 1 times 1 is 1, 1 times negative 1 is negative 1. You add them up, that's 0. 1 times 1 here is also 1. Then 1 times negative 1 also negative 1, that's 0. This is the result when we multiply a by x sub 1. We can also express this by a product of scalar 0 by any expression, because if you're going to multiply 0 to any entry, they will be 0. But of course, since we are verifying this, you have 1 and negative 1, that's your original given here. And we have represented the result by a product of your lambda sub 1 and your x sub 1 here. This means we have verified this situation. And for our last, so we're going to satisfy this. So you'll have, okay, you will have your a, which is 1, 1, 1, and 1, to be multiplied with your x sub 2, which is 1 and 1. The result of this should be able to achieve the result when we multiply lambda sub 2 and x sub 2 for it to be to satisfy as eigenvalue and eigenvector of the specific matrix here. So the result of this, of course, 2 by 2 matrix by 2 by 1, the result is also 2 by 1. 1 times 1 is 1, 1 times 1 is another 1, 1 plus 1, that's 2. 1 times 1, 1 times 1, add them up, that's still 2. Okay, if we are going to factor out 2, as this satisfies our lambda sub 2, the second eigenvalue, what retains in our matrix here is you have 1 and 1, which is also x sub 2. This means that the second pair of eigenvalue together with its corresponding eigenvector also satisfies the concern for the second matrix A. So this is how we do it in verifying eigenvalues and eigenvectors. The product of your matrix A and the corresponding vector should be represented or can be represented by the product of the corresponding eigenvalue and the vector to be called eigenvector. Okay, so this is all about for this video, and that is how we satisfy or verify eigenvalues and eigenvectors for 2 by 2 matrix. Thank you very much for watching.